All right, everybody, let's try this again. This is Lecture 2 in Engineering 216. I want to apologize for the initial recording. I'll tell you exactly what happened. I use OBS to record my lectures. It's the same software package that like Twitch streamers use and whatnot. And the way it works is you set up your microphone settings in advance. And so for class, I have it set to automatically record from my little Bluetooth lapel microphone. But I didn't change the setting when I came home to record my lecture in the evening. So I was talking up a storm and it was completely silent. So my apologies for the confusion. So we're going to take to this lecture again. So a couple of announcements, and some of this actually I already said in the email to the class earlier today, but I'm going to repeat it just to make sure that we're all on the same page. So the attendance grades are up to date, and what I said in the email was same thing I'll say here in regards to this lecture. We don't meet as often in this course as we did in, say, statics, and because I canceled class, I didn't want to really like punish you for that. So I decided just to count everybody present for lecture 2, so that and those grades are uploaded on Blackboard. For the lecture recording, I have since, I had said it in the video that it was on the YouTube playlist, but I was checking as I was uploading everything, and I don't know what happened, but for some reason it wasn't there. Everything now is on the YouTube playlist, other than obviously this video, but I'll post that here in a bit. This was not in the previous recording, but I will go ahead and say this now. I mentioned that I was working on getting a new room for the class, and I have done so. We are now going to meet in Corbley Hall, room 117. Initially, I wanted us to just move to the next adjacent room. The problem is that room wasn't big enough. We have 52 people in the class, and that room wasn't big enough to hold all of us. This is in Corbley Hall. It can seat 70 students, so it's got more than enough room for all of us. And there's a nice big old monitor right in the middle of the room. So I'm hoping that we shouldn't have the visual issues that we had last time in terms of trying to see what's going on. We should be pretty good there. Homework 1.1 was due today. Homework 1.2 is assigned today. You'll see that this is a fairly straightforward assignment and lecture, if you will. Ooh, I left my phone on. Let me turn that off. So what we're going to do is go through this topic of strain. And what we'll do is sort of, so today, last lecture we talked about stress. Today we're going to talk about strain. And then when we come back next Tuesday, we'll try and tie the two together. Because ultimately it is stresses and strains are how we're going to try and make engineering decisions about member selection and member sizes and things like that. But it is that relationship between stresses and strain that uniquely define how given materials behave. And you'll understand that after lecture 3. I do want to talk a little bit about class logistics though, just real quick. So let me go to this PowerPoint here. Let me hit escape. So if you open up Microsoft Teams, I just want to make sure that everybody is able to access this. If you open up Microsoft Teams, here in the very top, there is this where it says Posts, Files, and then it says Class Notebook. If you click Class Notebook, okay, what you should find is it should open up the OneNote for the class. If you look here, so what I want to show you is how to navigate the OneNote. So what you should see when you open up OneNote is a section called Content Library. And so if you open up Content Library, there's a folder there. And inside that folder, the folder says Using the Content Library. There's going to be a page for every example that we do in the class. And what I went ahead and did is the first lecture, we did that example on the board. I have since transposed all or copied all of those computations to the class notebooks. This is the class example that we did in class on Tuesday. I went ahead and put it in the class notebook for completion's sake so that everything's there. And because I've already recorded this lecture, the computations for today's problems are already done. So I guess once I start getting into the topic, this video might actually be a little faster than the previous recording. Plus, since I've already talked about it, you get better with repetition and whatnot. So with that, let me go ahead and just get back to the slideshow, and let's talk about strain. But before I do, I want to make sure that we're all understanding the definition of stress. So if we have a member under arbitrary loads, we talked about member response and how stress allows us to normalize the forces and loads on a given system because it helps to remove the geometry from the problem. Instead of thinking about forces, we're thinking about forces per unit area. Now, we didn't talk about this in depth, that we can define stresses that are not only normal to the plane but parallel to the plane. So in engineering design, we tend to look at not just normal stresses but shearing stresses as well. It's still the same idea. It's still force normalized per unit area. We will have specific applications where we look at normal stresses and shearing stresses throughout the semester. So to give you an example, when let's say we have a bar and we are taking that bar and stretching it or compressing it, those are normal stresses. But if we take that bar and twist it, those will generate shearing stresses. And so it'll be pretty easy, I think, as we go through the semester to identify context in terms of whether or not we're dealing with normal stresses or shearing stresses. But the concept is largely the same. Now, the stresses are good, but they're not enough to fully remove geometry from the problem because if I have a given bar or beam or pipe or whatever, the volume of those objects can typically be computed as the area times the length. And so stress serves to remove the area from the problem, but it does not remove the length. We need to remove the length from the problem as well, but in order to do that, we kind of need to talk about strains and then deformations. Okay, so let's talk a little bit about deformations. So this is a course focused on deformable bodies. The title of the course is Mechanics of Deformable Bodies. We should probably discuss deformation. So any engineering system that is subjected to external forces or applied loads or etc. will deform. Just, full stop. Okay. Even if it's subjected to its own self-weight, if it's subjected to external forces, whether they be occupancy loads, environmental loads, thermal loads, you name it. It doesn't matter. If you're taking a system and applying force to it, it will deform in response. In statics, we never really considered those deformations. And there is legitimacy to that from a static equilibrium perspective, because in engineering systems, while they do deform, more often than not, those deformations are small. We do need to understand them to understand performance of engineering materials. That's kind of the whole point of this course, but they are small. In order to explain deformations and explain strains and whatnot, I tend to use the example of a rubber band. And rubber bands kind of allow us to conceptualize them pretty easily because the deformations are really large. That would be a system that experiences large deformations. I can take a rubber band like this and stretch it, and it has a lot of deformation. So whereas if I take a piece of rebar and stretch it, I can generate a lot of stress, but I don't get as much deformation as a result. So let's talk about deformation. So let's take the example of a rubber band. So let's say I have a rubber band and I take that rubber band and I elongate it, okay? And I elongate it, let's say I make it 1 inch longer than it normally was. So here's the rubber band, I take the rubber band and I elongate it, and that amount of stretch, if you will, is 1 inch. So I would say the deformation is 1 inch, okay? If stresses serve to normalize forces, strains serve to normalize deformations. Essentially, the way it works is if, in order to compute stress, we're taking force per unit area, what we're doing with strains is we're taking deformation per unit length. So both stresses and strains working together tend to remove the geometry from the problem so we can look at each material and their performance individually. And so strain, in a nutshell, is a normalized measure of deformation. Now, I want to sort of specify this a little bit. I want to add a little bit of specificity. So if we consider a member before and after deformation, it is common in engineering land, especially when you're doing material testing. We'll see some of this in some testing videos I'm going to show you on Tuesday. But it is common to sort of identify the geometry before a load application and then after load application. So I have here an image, so on the left and right, so this is the element, if you will, before the load is applied, and this is after the load is applied. Now, what I've done here on this is I've drawn some little gauge lines, some guide marks, if you will. So we will say that this right here, this line, we'll call that delta x, and this line here, we'll call it delta x prime. Now, what delta x and delta x prime represent are the original length and the final length. So in other words, before I apply the load, the element is delta x long, and then after I apply the load, the whole bar gets larger, and then that element changes from delta x to delta x prime. Well, strain, the formal definition of strain, the sort of, mathematical expression, or the definition, would be the change in length over the original length. The change in length being the deformation. So to tether it back to the rubber band example, so remember I said the rubber band, I'm taking the rubber band and I'm stretching it, I'm making it longer. So let's say between my fingers, the original length is 8 inches. And then I stretch it and I measure, so it was 8 inches before, and now like this, let's say it's 9 inches. So if it was 8 inches long before and it's 9 inches long now, the deformation is the change in length. The 9 inches minus the 8 inches, or 1 inch. You got 1 inch longer. So strain is defined as the change in length over the original length. Now, one thing I will mention is that in stress land, the definition of normal stress and shear stress were largely very similar. We were taking force per unit area. The only thing that changed is whether or not we were looking at normal forces or parallel forces. In strains, the definition of normal strain versus shearing strain is actually somewhat different. Like they are different, and I think you'll see that when you look at the geometry. But so that we're clear, this definition doesn't quite hold for shearing strain, but we'll see that here in a second. Now, if you look at this this definition, so I have an average expression of strain, and I propose that the average expression in strain is the total deformation divided by the original length, change in length over the original length. And so a formula for that might be delta over L, or deformation over original length. But if we want it to be a little bit more mathematically pure, what we're talking about is this change in length over original length. We're really talking about a rate of change. If you go back to calculus and you say, well, what is the limit of delta x prime minus delta x divided by the original length, delta x? Well, if we're looking at infinitesimal expressions, or more refined estimates of strain as our element gets smaller, and we take the limit as that original length approaches 0, we're talking about the derivative. So I propose that if we have a function defining deformation as a function of x, and we want the strain as a function of x, just take the derivative of that, and that would yield the strain. Now, one thing that you really got to watch out for in strain computations is that strain is unitless. Okay, strain is a normalized expression of deformation, and it is a deformation per unit length. So going back to the rubber band, if it stretches 1 inch and its original length was 8 inches, then its strain is 1/8. But that's the point. The strain is 1/8. There are no units. Okay. Sometimes you will hear engineers say that the strain is so many inches per inch, or they'll say so many millimeters per millimeters. But the key is that strain is unitless. Unlike with stresses, where the units were psi or ksi or kilopascals or etc. So that's the definition of normal strain. For shearing strain, the deformation mode is different. See, with normal stresses, we're taking an element and applying a normal stress, and it tends to elongate. It physically gets longer, or it physically gets shorter. So we're talking about an actual, length along a given axis. We're talking about a change in distance. Whereas under shear, what tends to happen is we're not really talking about a change in length. We're talking about, or we're investigating a change in angle. So we're really talking about the difference between the original angle and the final angle, the change in angle divided by the original angle. Well, if you say the change in angular measurement divided by the original angular measurement, so if we look at this definition, our original angular measurement, if we're taking that to be something like 90 degrees, then our shearing strain expression would basically be this. This is kind of the same thing. We're just expressing it in terms of angles, and so that's, you see that pi over 2, because pi over 2, that's 90 degrees in radians, what have you. So it's basically the same approach. We're not going to use this definition directly, so don't get concerned about that. And as I said earlier, when we're dealing with shearing situations in this course, there are very specific formulas and expressions for stresses and strains, and it gets a lot more straightforward in those arenas. Okay, let's look at some examples. So I have 2 examples that we're going to go through with strains, and one of the things I will say before we actually start getting into the math, and this is something I definitely want you to be aware of in mechanics of deformable bodies. Strains typically are very, very small numbers. They are something like 0.00036 or something to that nature. So if you're ever doing a problem and you get a strain value and it's really small, I don't want you to think that that's an error. It's actually probably right. I know that sometimes when you're doing homework problems or exam problems, there's this feeling in your gut where you go, that doesn't look right. That doesn't feel like the right answer. But if strain values are coming out very small, that's okay. That's probably correct. So just want to make sure that you're aware of that. Because, again, as I said earlier, in engineering systems, the deformations tend to be very small. And if you're taking the deformations and dividing them by the original length, you're going to get a really small number. So that's okay. So for this first example, we've got a 2-tier pipe system. This is actually the same pipe system we did in example 1, or in the example on Tuesday. One of the things that I want to note about this example is we never used the lengths when we did the example on Tuesday. We never looked at them. All we had was, all we were interested in is the area. So we spent a lot of time computing cross-sectional areas and things like that because that mattered for stresses. Stress is P over A. But for strains, it doesn't. The areas won't really affect. All that matters is the lengths. Now, what we've been given for this problem is that the upper segment stretches 0.138 inches, and we know that the downward displacement at the bottom is 0.295 inches. And so what we want to compute are the resulting strains. So let's go to our class notebook and let's see what we've got going on with that. So I actually kind of already have some of it computed, but I just want to walk you through this. This is actually a very, very short example. This isn't very complicated. And one thing I will mention is that our introductory strain examples are not very challenging. They're very straightforward. And I don't think that strains really tend to be the most complicated portion of this course. They're actually pretty simple. So the biggest thing is just to make sure that you're using the right values, if you will. So recall that strain is the change in length over the original length. And if I'm trying to determine the strains in pipe 1 and pipe 2, I need the lengths and the deformations. Well, I've already got the lengths. Pipe 1 is 14 inches long. Pipe 2 is 16 inches long. So the lengths, good there. All we need are the deformations. And for the upper segment, we were given that. We were told that the upper segment stretches 0.138 inches. So its deformation is 0.138 inches. So if we know that its deformation is 0.138 inches, 0.138 inches divided by 14, that's the strain. Or sorry, if its deformation is 0.138 inches, 0.138 inches divided by 14, there's the strain. Now, for the display, for the deformation of segment 2, it's not 0.295. Okay, you got to read the problem statement. What the problem statement is saying is that determine the strains if the upper segment stretches 0.138 and the total downward displacement at the bottom is 0.295. So what's going on is what we've got over here on the left. So what we're basically saying is that junction between pipe 1 and pipe 2, it drops 0.138 inches because that's how much the upper pipe stretches. But the bottom point goes down 0.295. So here's the pipe system. This bottom point drops down 0.295 inches. But remember, some of that is the upper pipe stretching, right? The upper pipe is stretching 0.138 inches. So the question is, how much does that lower pipe stretch? And it's not 0.295 inches because some of that is the pipe just going along for the ride because the upper component stretched. Really, the deformation in the second pipe is the difference in those two. See, I propose that the first pipe stretches 0.138 inches, and then the second pipe stretches 0.157 inches, right? Because if you add those up, that's a total of 0.295, which is how you get that bottom downward displacement. So if you have the deformations in each segment and you have the lengths of each segment, strains are pretty easy to compute. And as I said, the strains, look at those numbers. They're pretty small. If you take 0.138 and divide it by 14, or 0.157 and divide it by 16, you get some pretty tiny numbers. And that's okay. Strains are small. That is normal, okay? So yeah, I think in the original video, I probably spent a little bit more time doing this because I was writing everything out. But with this, because I already wrote it out, I think this video will be a lot faster. So for those of you who are watching this, it'll make for a shorter watch. Okay, so let's talk about problem 2. So this one's the one that's maybe a little bit more involved. So I'm actually going to erase this stuff over here a little bit because some of this I might redraw and reference. So what we have here in shape 2 is a rigid beam supported by these two bars. Now I want to take a full stop and discuss this a little bit, because right off the bat, I think I might sound like I'm violating one of my rules in this problem, because I said every system deforms. Every system experiences deformation, and that's true. Everything in this world, every element that experiences load will deform under that force. However, the big thing to keep in mind is the relative displacement and whether or not an object can be considered analytically rigid or not. One of the advantages of considering analytic rigidity is that more often than not, it makes the problem more, it actually makes it simpler. Let me give you an example. Let's go back to the rubber band, okay? So remember, I have a rubber band. I have this rubber band between my fingers, and I'm stretching my fingers, okay? What if instead of between my fingers, what if I put the rubber band between two steel rods? So I have two steel rods, and I have a rubber band between them. If I take those steel rods and I move them like this, I am going to stretch the rubber band, okay? The rubber band is going to deform. Now, here's the thing. I propose that rubber band is also exerting force on the steel rod, and the steel rods are undergoing deformation. But those deformations are so infinitesimally small compared to what's going on with the rubber band that we can just assume they're negligent. They're negligible. We don't need to consider them. We can assume those steel rods are rigid when compared to the flimsy little rubber band. So it is advantageous as an engineer to just say they're rigid. It's okay. They're not deforming compared to the deformation experienced by the rubber band. And so that's kind of what's going on here. I'm assuming that the beam, that its stiffness is so much larger than the two bars that are supporting it, that we're just going to consider the beam rigid. Okay, so the beam is supported by a hinge on the left and two rods, B and A. Now, what we see here, we have all the dimensions laid out and what have you, and with this problem, what we're told is we know that we have this load P here on the left. So this load P is going to generate deformation in the system. It's not going to deform or change the geometry of the beam, but it will cause axial stretching of the bars, the two rods A and B. Well, if I know the strain in rod B, in bar B, is 0.006, I want to determine the strain in bar A. Now, one final thing before we get into this problem. I am assuming that the beam is rigid. Later on, we will not. We will learn how to compute beam deformations. And beam deformations are far much more involved than axial bar deformations from a math perspective, because all bars tend to do is get longer or shorter along their axis. So the math to define that relationship is actually pretty straightforward. But for beams, I believe the math is straightforward as well, but it's, I'd say, less straightforward than that of a bar. because with beams, we have loads that vary along the length, and we have deformations and rotations and whatnot that vary over the length. So the functions and the math that we have to use is a little bit more involved. But we'll talk about that probably March or April time frame, something like that. Let's talk about what the bar is going to do. So if the bar is rigid, okay, if the bar is rigid, then, or sorry, if the beam is rigid, and we have a load here, P, that's applied over there. Now this is load P. What's that going to do? It's going to cause that to drop down. So what's going on here? Well, I propose that both bars are going to stretch some amount. Like if we look here, if this is what the bar looked like before, or the beam looked like before, and this is what the beam looked like after, those rods are stretching, okay? Let me undo my highlights. I'm going to use my highlighter here on this problem to help point out what's going on. So I propose that these distances here and here represent the deformations in the bars, okay? Because think, here's what the bar was like before. Let's take bar B, okay? So here's what the beam looks like now. So here's the original length, and here is the final length. And I know I'm sort of, my art is horrible there, but that right there is the original length, or sorry, the final length. That is the original length. So this dimension right here, that's the deformation, okay? And that's actually what I have drawn down here at the bottom. And so what we need to do is we probably need to see if we can figure out what's going on with these deformations. Now, in this problem, okay, if we look at the problem and what we were given that the strain in bar B was 0.006. And we know that the original length of bar B is 36 inches. Well, if I know the strain and I know the deformation, well, if strain is change in length over the original length, or deformation over L, I can determine that deformation by just strain times L, epsilon times L. So epsilon is our Greek letter for strain, delta is our Greek letter for deformation. Strain times original length, and I get a deformation of 0.216 inches. Now, why am I getting inches? Well, the reason I'm getting inches is because of this right here. I converted the length to inches. Now, I'm going to stop right now and say that for this particular problem, it is probably unnecessary for me to do that conversion. Just, full honesty. It's not necessary. However, I'm doing it here. And I'm doing it here because I do want you to get into the habit of being unit conscious in later problems. In this course and in mechanics and materials in general, being unit conscious is much more important. In statics, if I'm being honest, you needed to understand the units that we were dealing with, but honestly, unit conversion was never really too big of an issue, because if you have a sum of forces system, everything's in newtons, right? So there's no real need to convert anything. But if you're going from forces to stresses to strains to deformations, etc., you got to make sure your units are consistent. For this problem, it's really not necessary mathematically to convert that to inches, but it will be on later problems. So I want you to get into the habit of doing that and making sure that you're consistent when you're looking at strains. Because here's the deal, and here's the sort of the crux of what we're talking about with these units. Let's take a simple example. Let's take a beam in a building. If I asked you how long that beam is, your answer is probably going to be in terms of maybe feet or meters. Like that beam is 20 feet long, or it's this beam over here is 8 meters long. So you're expressing length in feet and meters. Now if I asked you, okay, that beam's deflecting, how much is that deflection? Well, you're probably going to say that deflection is so many inches, or that deflection is so many millimeters. And right off the bat, there's a mix-up with units, right? There's a difference between member lengths and deformations. You're expressing them in different units. And so I want you to get into the habit of converting to consistent units, and that's why I've done that here. Okay, so we know now our displacement at B is 0.216 inches. And so the idea now is, because this is a rigid bar and it's deforming in sort of this linear fashion, well, here's the deal, right? The deal is we have a right triangle. We're basically looking at slope ratios, right? I propose that the slope ratio from, let me put the highlighters out. The slope ratio from here to here is the same as the slope ratio from here to here. That's what I'm assuming. That's sort of what we're taking into account when we're trying to compare these deformations. And the reason I'm able to do that is because the bar is analytically rigid. If the bar is analytically rigid, then it's not going to flex. It's just going to drop down, and we're going to have this linear relationship. So I propose that we can compare the slope ratios of these two. If I know the deformation at B, I can determine the deformation at A. And see, I propose that the relationship is delta B is to 3 as delta A is to 8, right? So if I just figured out delta B, I can rearrange that. Delta A is 8/3 of delta B, and plug and chug, and I get 0.576 inches. And so if I know that is 0.576 inches, and I know the length of bar A, the original length of bar A is 48 inches, strain is changing length over the original length, plug and chug, and I get 0.012. And that's it. That's the strain. And so if you actually look at the strains, the strain in bar A is double that of double that of the strain in bar B. So is that a good thing? Is that a bad thing? Well, depends on the materials, depends on those relationships. See, these past two lectures, what we've been doing is we've been trying to define stress and strain, but we've been defining them independently, right? So here's this concept of stresses, here's this concept of strains. What we're then going to do is we're going to take those two concepts and marry them together, okay? And understanding the relationships between stresses and strains, that's how you determine material behavior. And so that's going to be the focus of the lecture next Tuesday. And since our examples are already done, I'm actually going to call it a little bit early. That's all we've got, because we've got our examples completed and our definitions done. I have homework 1.2 posted. It is a similar problem. Problem like the last one. It'll be in the same fashion, the quiz format, if you will, on Blackboard. I might talk about on Tuesday if we want to keep doing that, or if we want to do the homework upload, whatever we think the class is easiest. There will probably be a little bit of a mixture of both throughout the semester, but I will keep you posted on that. With that, that's all I've got. I'm going to stop the recording. I will see you all next week. You all have a wonderful weekend. We'll see you when you return, bright and early at 8 a.m. All right, that's all I got.